Let's get started. I think the first session was very interesting. I hope that all of you are having fun, which is the intention, and you're learning. I'm learning a lot, and I'm looking forward to learning even more. In this second session, we're going to discuss how to unlock the hidden value of sustainability. We're going to see about 3 really interesting projects from 3 different people working on passive housing and energy efficiency, and also biophilic design. And Professor David Su is going to moderate. Professor David Su is an associate professor at the Department of Urban Studies and Planning here at MIT. He was previously at the faculty of the Graduate School of Design at the University of Pennsylvania. Professor Su is a world-known leader in the research of building efficiency, so no one better suited to lead this session. So David, whenever you're ready. Thank you.
Thank you very much for joining us for this session. I'm really excited to hear from all 3 of our terrific speakers. I guess I'll just kind of start off the session by talking a little bit about some of my work in energy efficiency and research in energy efficiency, if only because I want you to picture a curve. And it's a very simple curve. It's just the bell curve or Gaussian curve. And the curve is basically how we think about how people adopt technology. So you're all probably pretty familiar with the phrase early adopters. This comes from Rogers, has this kind of theory of the diffusion of innovations. And I think of energy efficiency in buildings as this kind of diffusion of innovation curve. We have the early adopters, the cutting edge, people who are adopting new technologies. We have a kind of a broad middle that adopts the technology more slowly, and then we have laggards. And so the reason why it's important is because buildings embody technology. Buildings are long-lived, they're durable, they're expensive, they're really big, and you can't really move them around. And so once you build a building, that technology lasts for a long time. And so we have to think in terms of how we do research, how we do policy, how we want to change the market, in terms of this very real, very permanent landscape of buildings. And this is kind of a landscape that changes at fairly slow cycles, except in the real estate market, if people like all of you start to understand or basically pursue these kinds of goals, then we'll actually see buildings become more energy efficient. And the reason why that's important is because I start basically every single one of my papers by saying 2 simple things. About 40% of the primary energy in the world is consumed through buildings, and 30% of all greenhouse gas emissions are also emitted basically through building-related activities. So this is to say that all of our policies, all of our efforts, all of our markets, all of our market incentives, the structure of our markets really have to act in a long-term way to try to basically encourage this very large pathway for energy consumption and greenhouse gases to become more and more sustainable over time. But it's also a challenge. I will just kind of take a little moment to talk about a personal anecdote. I took a brief detour working in real estate finance about 15 years ago. I often say that the best thing I got out of it was a couple really good friends. But I actually looked up one of my old friends, and he described sustainability as this thing, he knows I've gone off to work on green buildings, energy efficiency research for the last 15 years after working together in finance. And he still called sustainability, in one of the articles he wrote, a necessary evil. And so this is actually, in my mind, the challenge. We still have to go quite a bit to convince some people in the real estate industry that it's actually a necessary good. And so I want to introduce all 3 speakers as people who are really working at the cutting edge to move that whole kind of curve, that whole mass of buildings towards the cutting edge. They're helping to overcome some of the barriers that already exist, both in market structure and incentives, and frankly, lack of knowledge about what really cutting edge or energy efficient or green design might be. So with that, I'll actually I'll introduce them each before their talk, but let me start off with Bill Browning. Bill Browning is an advocate for sustainable design solutions at all levels of business, government, and civil society. Early in his career, Bill built Buckminster Fuller's last experimental structure, and in 2006, he co-founded Terrapin, Bright Green, an environmental strategies research and consulting firm. He's a founding board member of the USGBC. In addition to consulting, Bill writes and lectures widely on sustainable design and building practices. And he also, most notably because we're here, holds a Master of Science in Real Estate Development from Massachusetts Institute of Technology, where he was awarded the MIT Center for Real Estate's 1991 Public Sector Fellowship. He's done many notable things since then, working with Disney, New Songdo City, Lucasfilm, Google, Bank of America, the White House, and the Sydney 2000 Olympics. He's authored a number of books on biophilic design, but I'll let him describe his work now. Let's give him a warm round of applause. Thank you. If you'd like.
So a little context. When I graduated here in '91, I went back to Rocky Mountain Institute and we started a group called Green Development Services. And we were collecting case studies of early green buildings to eventually write a book on what's different about green development than conventional. And in the course of doing that, we started finding these fairly radical jumps in worker productivity and sales per square foot and pricing and such that was being achieved in these buildings, and could find nothing in the literature about that. And so that led to us writing a publication in 1994 called Greening the Building and the Bottom Line. As we collected more of those case studies over time, that led us to ask the question of what would it be in the built environment? Because we realized that these jumps in productivity were maybe just placeholders for something more important going on with the people in these places. And that eventually led us into an orbit with E.O. Wilson at Harvard and Stephen Kellert at Yale and Judy Heerwagen at the University of Washington and Roger Ulrich at Texas A&M, who are all doing very early work on human connection to nature and what the impact that had on us both psychologically and physiologically. There we go. So our work in Terrapin, we're a small research and consulting firm, is really in a variety of areas, working on complex green buildings, working on ecosystem metrics for gauging performance of a property, and working with industrial design on solving design problems that traditional engineering hasn't been able to solve. But if we can find biologists who can find something in nature who has figured out how to do that, apply those lessons to that. And then the main area on health and well-being being biophilic design. So this is the working definition that most people see from Ed Wilson. And it's really about an innate connection to nature. And the science, a lot of it is coming out of environmental psychology. It's coming out of increasingly out of neuroscience experiments on looking at both physiological response and brain pattern response as people are having these experiences. Most people probably think when you describe bringing nature in the built environment that you're going to default to plants and water, right? Which are good strategies. Don't get me wrong, those are good strategies, but there are two of a menu of about 15 different experiences that we've cataloged into a pattern language. Why is this all important? Well, Rocky Mountain Institute, we were always focused on that first number, energy, right? Because that's an easy one to calculate in a green building, energy savings and the returns on that. But that tends to forget the real cost of a building on an annual basis, particularly an office building, is the people. And so 1% gain in productivity is our entire energy bill. So why not address both simultaneously? What we found in combing through the science over the last 20 plus years is that all the experiences fall into three sort of big categories. The first are what we call nature in the space, which are direct experiences of nature in the built environment. Natural analogs are representations and indirect experiences, and nature of the space has to do with the three-dimensional characteristics of the space and how you respond to that psychologically and physiologically. Here's the pattern language that we've developed. You don't have to memorize it. I have cards for everybody. And you can download all this information from our website. So here's some examples of nature in the space. Presence of water one is a really increasingly interesting one, particularly as we're getting into issues around acoustics and psychoacoustics and how people respond to sound and noise in the built environment. Analogs. We have a really strong preference for natural materials, and the neuroscientists aren't quite sure why. It may be because when we see a piece of wood, we do a semantic jump that goes wood, tree, alive, or we're just addicted to fractals. Fractals are really brain candy, particularly fractals that occur in nature. We're fascinated by them. And you look at a piece of wood, it's layered fractals, right? And the piece of wood next to it's not the same. Maybe similar, but it's a different pattern. So these are the spatial characteristics, nature of the space. So prospect is an unimpeded view through space. It's really important for wayfinding, perceptions of safety, and stress reduction. Refuge is where my back is protected and I have some canopy overhead. Now, if I can put prospect and refuge together, like when you go into the restaurant and you have your choice of any seat in the restaurant, and it's a series of rounds in the center and high back booths on the perimeter, how many of you want the booth? So what you're getting there is you've got a refuge condition and you have a prospect view across the entire restaurant, prospect and refuge. Mystery is partially revealed information. Some of the scientists we've been working with who investigate this one say, you feel compelled to go investigate what's beyond that. Now, mystery, most people think is a visual condition, but it frequently, think about that bakery down the street. You smell that well before you can see it and you get to it, but you just gotta go look in that window and see what, right? Mystery. Risk peril is a fun one. It elicits a dopamine response, but it's one you don't want to use too much of in the space. This is the Riverwalk in San Antonio. The water's not that deep. Yes, you might fall in, but that's not really all that dangerous. So 14 patterns from, coming from a design background, 14 is too many to remember, right? And too many to select from. So in our work, and particularly in the work for the last 7 years, our research has been supported by Google and the development of metrics for their buildings and campuses worldwide. And so for them, the way they use this is what they are calling outcome-based design. I look at the users of a space and I look at what's going on in the space and I say, what's important? Is it stress reduction? Is it cognitive performance? Is it emotion, mood, and preference? Is it enhanced creativity? Not all the patterns support all those outcomes, and so it allows me to filter which ones might be most appropriate candidates for the space that I'm working in. Now, just having the patterns for us isn't enough. We want to see how people are actually responding to that. So we do a fair amount of post-occupancy, and we're moving into observational studies, and we're moving into some neuroscience experiments as well to support this work. So this is an office that we used to share with Cook Fox Architects in Chelsea in Midtown Manhattan. The primary green feature, the biophilic feature here, was this view to a 3,600 square foot green roof. And you can see it's at the level of the window, so pretty much every desk in the space had a view to that. Now, it wasn't entirely successful. The prospect view and the connection to nature was good, but this was a space that was entirely open space and almost had zero experience of refuge. The few operating refuge conditions were these conference rooms down here that were always in use. So to get a refuge experience, you had to go out into the stairwells or out onto the roof, neither of which were highly desirable. So when Cook Fox moved into a new space last year, they then did a balance of prospect and refuge conditions. Now, in the survey and the stress mapping, it's no surprise that number 9, the area of highest stress, was the one place in the entire office where there was no view to the outside. Now you would think that zone 1 would be, with the best view, would be the lowest stress, but that's also the zone where everyone coming off the elevator and going to the reception and walking to the partner's office in the other conference room went past that. And so that's the one section that had the highest number of interruptions. We last fall published a study of biophilic design and how it impacts hospitality. We looked at pricing, we looked at which patterns are used, and then we did an observational study of does it change the use patterns. And so part of that was we picked 6 hotels in Midtown Manhattan, 3 which were conventional and 3 which had biophilic design components. Thank God for interns. We had folks sit in the lobby in the morning, in the afternoon, in the evening, recording patterns. And what we were looking at was transient, passive user, active user. In the biophilic hotels, we saw a 36% increase in the number of active and passive users. Now that's really cool and interesting for us, but we want to take that a next step, and so we have a partnership with the Cloud Lab at Columbia University. We're still fundraising for this, but we are going to wire people up and take them on a walk from Times Square to Central Park. And neural cartography is, as your brain state changes, the pixels on the map underneath you change colors. And so the pixels are an indicator of what brain state you are in: agitated, focused, meditative. What state are you in? Attentive. And you take about 40 people through that experience, so hopefully you get 27 good data sets, and you layer them on top of each other and see if your spaces are inducing a common result. If you want to see more about this and case studies and all of this stuff is on our website, terrapingreencom.
Great, thank you.
Assume that's forward.
That was a very quick tour of a lot of deep research. We'll have a lot more time to talk together once we go through the presentations. But I want to introduce Blake Middleton. He's a partner at Handel Architects. He's the lead designer for some of the firm's most prominent work and very well-known work. Blake's expertise is the hybrid mixed-use building as a catalyst for creating sustainable, revitalized neighborhoods in dense urban environments. Recent examples include the house at the Cornell Tech campus, which I think he'll talk about today, and the Millennium Tower Boston, a 1.4 million square foot mixed-use tower, including the renovation of Daniel Burnham's landmark Filene's building. There's a number of projects that have built on his firm's experience at Cornell Tech, which I think we'll see. But Blake has taught and lectured widely, and his work has won distinction from the AIA, SARA, Urban Land Institute, and the Congress for New Urbanism, and his designs have been published widely and exhibited nationally. Let's give him a round of applause. Thank you.
Thank you.
Great. Thank you.
All right. So, can you guys hear me okay? I'm going to blaze through 50 slides in 5 minutes, so we'll see if I can. He's a strict time master here. And we're going to shift gears a little bit, and we may dive into the weeds also. So for the architects, engineers, and builders here, this stuff will probably be very clear to you. And for those that aren't, it's really, there's a message behind all of this, which is really to take the fear factor out of one level of a pretty powerful sustainable design approach to large buildings. I think I'm going to be preaching to the choir here, so I'm going to move through this quickly, and you'll hear lots of statistics, I'm sure all day long or for the last 2 days, about carbon emissions and the impact there. The point of all this is that the goal is to reduce this significantly. We in the building industry have an opportunity to make a dent. There are bigger factors in terms of the production of CO2 in cities, certainly around the world, but buildings contribute a fair amount. These are some interesting statistics just in New York City alone. I had to talk to a Harvard climatologist, a friend of mine, who I kept saying, how do you picture tons of CO2? I don't understand how a ton, what shape, how big is it? So this was an interesting little diagram to sort of take the 35.7 million tons of CO2 and how big a volume that thing actually encompasses. It's kind of frightening thought. But there are huge, we've made such incredible progress in the last decade even in terms of energy efficiency, doing radically more with a lot less. And it can be seen in all sorts of applications in our daily lives, I think. Someday, most of us will be driving electric cars. But this sort of progress is rather substantial. What's interesting about the application of Passive House as a design protocol for buildings is these statistics right here. An average building in New York City, for example, and Boston and other cities in the Northeast, I think, sort of follow suit, of a fairly large size, use 140.8 kilobTUs per square foot per year. And that's sort of broad index, but that's a substantial amount of energy. And what Passive House requires as a basic prescription is to reduce that energy demand in a building over that same period of time in the same area down to 38.1, which is a substantial reduction, as you can see here. It's a performance-based, not prescriptive approach to designing building envelopes. It's about essentially designing a high-performance building envelope. It requires constant fresh air to be brought into the building as a consequence of this really tight envelope. Heat recovery is also required. And then probably most importantly, what for me is really interesting is just the application of what I consider to be off-the-shelf technology. There's nothing exotic about a passive house. I'm not sure whether my colleagues will agree with this or not, but it's really how you put the building together, how you design it and engineer it initially, and then actually how you physically build it and then eventually operate it. And the impacts can be quite substantial, in particular for user comfort, which we've heard a little bit about already, and we'll probably talk more about later. I'm not going to get into the statistics here. Welcome to share this information after the talk is over. Let me talk about Cornell. So the Cornell Tech campus just opened its doors last September, sort of completing its first academic year in business, so to speak. It's comprised of three major structures, a kind of co-location building, which is sort of the building there in glass on the right, the Bloomberg Center, which is the campus classroom building on the left, and then the house, which is what I'm talking about, which is the residence building for these students, which are all graduate students, postdoctorates, and faculty also. The building is situated on Roosevelt Island, which is a very narrow island in the middle of the East River, water on both sides. There's stunning views there. The building's about 270,000 square feet, 26 stories, 270 feet tall, and about 500 beds needed to be designed and occupied in here. Essentially, it's a conventional New York City apartment building, and it put together in an unconventional way. And some of the basic precepts behind all this has to do with, with Passive House, has to do with orientation, compact building form, how you design that enclosure, that all-important wrapper around the building, the developing a low-energy system for air handling, appliances, all of these elements in the building. In an apartment building, we have 360 kitchens, for example. All of this has to be, and lighting, all of this has to be looked at very carefully, and then of course user-friendliness and the interface for all that. So the big difference here is really how the envelope of the building is designed. We ended up calling this sort of the wrap, and it's all about developing a highly insulated, thermally broken or disconnected from the interior structure to minimize the transfer of heat through the building envelope itself into the structure, in both directions. I'm going to fly past this. We talked a lot about the kind of testing that's involved, which is substantial. You have to take it a degree higher than you would a normal exterior wall for a building of a typical size. It's one of those airplane engines to push the wind and the water on the building. Lots of sensors involved to really understand on a performance mock-up to make sure the panels, which are all prefabricated, and the reason for that is to get the sort of high quality assurance you get in the factory that you don't necessarily get in the field. I'll talk more about that in a second. So the idea was to wrap this building in a series of prefabricated panels that were fabricated in Pennsylvania and shipped by barge actually to the site because of its location of the water. And you can see a picture here of the panels going up around the building frame. So it's just a very straightforward concrete high-rise building in New York. But then the real trick in that envelope, and this is one of these kind of diagrams, is the continuity of the air barrier itself. You have to plug every single microscopic leak around this huge perimeter. I should also say nobody had done a building of this type, this big before. There had been a 20-story high-rise in Frankfurt that had been completed, I don't know, 4 or 5 years before, meeting passive house requirements, but that was an office building, not a residence. This is all about how you put it together. The contractors had to kind of keep an incredibly, sharp eye on what's going on. You had to have the builders actually buy into quality control at a much higher level than what they were used to. There was a lot of theory about how we were going to prefab the panels, and that green stuff is part of that air barrier, and the whole thing would be covered, and you don't have to sort of tape and seal 4 joints around it once you've got it in place. But then we discovered, you see these little points above there, those are the connection points of the facade to the structure, and it turned out to be a lot easier not to put it all on, but rather do that in the field. So there was an immense amount of learning going on in this whole process, in particular for the builder, and having much more sort of on-site accountability in terms of the construction process to keep track of all of this. And the blower door test is what they do, where they sort of pressurize the building to find any of these leaks. And nobody had done it this high and this many floors before, so we had to test it on several floors, use that as the sort of find out where all the sort of weak spots were, plug those leaks, so to speak, and then apply those lessons learned for the contractor all the way up through the rest of the building. Cross your fingers and hope that when you then do the blower door test for the whole building, that you actually pass that, because that's one of the requirements for passive houses, actually, is to meet a certain very tight level of airtightness for the building. These are some pictures of the final blower door test. I was trying to figure out whether I should stay in town or get out of town when this was going to happen. Turned out we did 4 times better than the requirement. They cared that much about how they put it together. We sort of covered all the details that we had to go through. And so it was an astonishing sort of performance for the building. Heat recovery is used both for air ventilation with 2 energy recovery ventilators on the roof of the building. You pump fresh air into all the spaces of the building, preheating, pre-cooling. And at the same time, because you've got such a robust envelope to wrap the building, you need very little heat. In fact, one of the problems that we encountered was you couldn't find an evaporator, which is where the coolant heating medium, which is called a VRF system, running to every single room. We couldn't find one small enough. They only made 1-ton units. What we want to have somebody do is market a 1/4-ton unit. So here's some pictures of the completed building, one of the typical apartments. And I'll say a little more maybe during the question and answer about that. What's really interesting for our practice right now is we're actually applying. That was great to have a beta test there. We lost our shirts in terms of the fee, but it was a fantastic learning experience for us. And it led to now being involved with a project called Sendero Verde, which is almost 800,000 square foot mixed-use, high-rise, 100% affordable housing in East Harlem, New York. All the residential component of the building will be passive house also. There's some statistics on this project. We're taking it to scale, but having to do it for less construction costs than the Cornell project, in fact. All these things are driven, in this case, by rents. These are all developer-driven projects. These are not institutional projects. They're not privately funded. They're bank-financed. And that's, I think, an important thing, which I hope we have some time to talk about afterwards. It's applying high-tech in a low-tech way, using low-tech systems here. I don't have time to talk about all this other than much different process of creating the air barrier around the perimeter of the building in the field. It's not prefabricated. It's a block and plank building. Very straightforward. We tested, one thing that was interesting to see whether or not we could use a prepackaged heat pump, which had a ventilator for every room, and then discovered and thought, oh, this is fantastic. It was the coolant system for the cooling tower on these things would be way less expensive than using a VRF. The problem is once we tested it, the thing leaked like a sieve. So we said, no, we'll stick with the VRF. Here in Boston, we're applying these lessons in a much different way into a 650,000 square foot office component at Winthrop Square, 115 Federal Street. There was some discussion that Bill was just talking about in terms of the office environment. Some of that thinking has been going on already now. This is a commercial office building. Again, it's not built to suit. We're designing the office component as passive house. It's using a curtain wall, not a brick and block system. This is kind of the interior environment. The market here is looking for a loft-like spaces, a lot of glass. How do you manage that? Because typical passive house buildings need to be maybe in the 40% range of glazing. Love to talk more about this. We've been working with John Fernandez, who's a professor here at MIT. talking about sort of, comfort in the work environment. This is, creating comfort right on your wrist and or in the hyper chair, which is it's all about sort of local climates. So we're starting to look at those as other ways to enhance the work environment in that regard. We've applied some of these, the knowledge that we've gained through here at a competition we've been doing at University of Toronto, which I'll skip over other than it's 750 beds. That's the typical plan. It's quite dense in terms of the way it works. These details are a little hard to follow other than to say it's a metal panel system, prefabricated, but then the exterior walls then applied with all that insulation, that kind of gridded stuff you see there, how thick that wall gets. Where are we going? I think the main message here is that a lot of this work is really starting to take off at scale. No longer a passive house kind of single family houses or maybe low-rise 8-story or even 8 units per building. These are much larger projects happening around North America. This is the trend, which I think is really important, and we see that are continuing to curve up. And the cumulative square footage, actually the projects we're doing alone, I think will add another, double the amount on that right-hand thing for 2018. We used to build walls a long time ago with windows, and they were highly thermally efficient in a certain degree. Something happened in the 1920s that kind of changed our perspective about buildings. There are a lot of fantastic technologies for doing double wall construction and sort of high performance buildings, but they're also high tech. And some of them require a fair amount of energy to operate and certainly to build. And our point here is that there's a whole other way to go about this. It can be a low-tech, off-the-shelf technology to produce really fantastic results in terms of energy performance. Thanks.
Great. Thank you. Again, a wealth of knowledge and detail that we'll be able to discuss more. Our last presentation is by Robert Hutchinson. He has 30 years of experience in energy research and business strategy and decision making. He's a senior fellow at the Rocky Mountain Institute, working across all energy use sectors to support specific RMI priorities. He's a particular interest in impact-focused entrepreneurship and design and decision-making processes, decision architecture, so to speak, including new financing models. He was previously a partner and director with the Boston Consulting Group for almost 20 years, where he focused on starting 2 of their global practices in energy and IT. So let's welcome to the stage. Thank you very much. Thank you.
So Blake and I plotted for months about how not to overlap. Just kidding, we just met, but we won't, in fact, overlap because I'm going to try to plow the middle ground between what Bill and Blake have talked about, where Blake got right to some of the nitty-gritty of what changes when you take a sustainability framework. What might you do that's different? And Bill really said, what should you do, whether it's different or not, because it gets you something way, way, way better. And so I'm just going to talk about an example and some of the things we learned. Now, RMI has basically been a consultancy slash player in the buildings world, since the early days of when we were trying to figure out what sustainability meant. And we finally had a chance a few years ago to build our own office. It is near Aspen. It is a cold place. It's in the middle of a big field next to a river. It's the site. We were able to orient things properly so that we got the right amount of sun. We have a fairly extreme climate, particularly in winter, but we also get those huge temperature swings, 40-degree temperature swings, quite regularly over a matter of sometimes a few hours. So when you're trying to say, we want to build a leading building, we want it to be an example of all that engagement with the buildings world all this time. We know that people will continue learning past us. We want to have it be institutional grade. We want it to perform well. In our cold climate, we want it ideally to be passive, and we were able to quite straightforwardly meet both the passive house specs, but also run with passive heating and cooling. And I'll get into a little bit more exactly what that means in a fairly extreme climate. And last but not least, how do you do one of these things? How do you do a building when you're doing some R&D, you're doing some supply chain development, you're doing some build your own gizmos, What sort of contract structure do you have? How do you team? How do you organize that? As an ex-business consultant, that was one of my biggest focuses, was how do I construct an environment where no matter what happens, and you know what is going to happen, no matter what happens, I will be harnessing, essentially all the energy of this great team I've put together to not only figure out what the problem is, but solve it, and to maybe find something even better because we engaged with that problem, as opposed to any time whatsoever on the risk and the downside of that. Trying to figure out whose fault it was, trying to figure out how to pay for it, all that stuff. So we said, okay, we're going to structure this in such a way that we get the maximum amount of attention on the right stuff. And oh, by the way, we're going to try to make sure everybody makes money. What I didn't tell the architect and contractors, that having been having structured all sorts of deals for many years, I also knew that the IPD structure we used was the risk minimizing one for me as the owner, because it gave me basically an absolute ceiling on what I'd have to pay up to a given point. So I may or may not get to that near the end of this, but I wanted to make sure that you heard that every element of how you develop and execute a project is actually a designed construct, and you can change an awful lot of the pieces. You can change the financial structure, you can change the contract structure. Those are all things that you design. And if you're in the position where we were as a small nonprofit with a brand around innovation, we were going to change everything we needed to change in order to get what we wanted. So as you think about expanding the framework of what can sustainability do for you, do not forget some of those structural issues, as opposed to it's just about the better technology. On the technology for a second, getting to zero, pretty straightforward. We're well beyond net zero at this point. You start with an energy budget with whatever energy technology happens to work for you, and then you keep at it until you get below that. It's what we did. We're there easily. We chose to go passive. It's not necessarily the cheapest, but it has some interesting side benefits that I'll get to in a minute. We basically insulate the jabbers out of it. At one point, the building looked like the Blue Man, covered with that liquid air barrier all around. We didn't quite get as good as Cornell. We're 3 times as good as Passive House air infiltration, not 4. Somebody must have drilled a hole somewhere. But it's very, very tight. Works well. Basically, we are solar heated into thermal mass. We're also thermally cooled into that same thermal mass, and I'll get into that a little bit more in a second. Energy performance-wise, I would highly encourage, now that the tools are getting a lot better and a lot cheaper to run, I would highly encourage modeling. The little green lines are what our model told us we would be doing, and we're doing it. The models work. We had to teach our ME consultants how to do the modeling. We had to teach them a whole new program, because the one they're using couldn't do these passive constructs. So our ME not only learned a new model, but became the owner of a world-class design using the new model in a short amount of time. People want to learn new stuff. They want to do new stuff. So if it's something else you want to change it. And we are below our modeled energy by a couple of kBTUs. We're at just under 16 kBTUs per square foot. So a little bit under half what the New York situation is in a worse climate. So we basically swaddled it in more insulation than they did. We have a wonderful energy profile, and I'll get back into what you can do with this sort of energy profile in a little bit. It won't look this good at the point when we have a full fleet of electric cars, but part of our sizing was we charge a fleet of electric cars with our building, and use the timing of that to manage our load. Right now, we're nowhere near our demand charges, but when the time comes when we are between that and the batteries in the building, we'll never pay a demand charge. And we'll also be a good grid citizen, which is a phrase I'd like to see if it catches on or not. Buildings are part of the grid. If the buildings do what the grid needs, over time you can get paid for that. Right now you can get paid for it if you happen to be up against a nasty demand charge, which a lot of us are. One of the keys, if you're going to run in the way we run it, is the people in the building. If you see, about something just over 40% is space heating and lights. Even those are affected by occupants in a big way, but virtually everything else is essentially stuff that occupants turn on and off, or it's something that supports something that the occupants turn on and off, or at least leave the door open or not, the fridges. One of our biggest single electricity users is in fact our video conferencing, because we didn't have a way to spec that down as much as we would have liked. The next generations are getting better. Cisco will be replacing that soon with a better one. But if you can think about it, engagement with the occupants when you get down into this rare air of 16 kBTUs per square foot, it's all about the occupants and the plug loads and what gets plugged in, and so we control that pretty carefully. Part of the control is frankly just making it all visible. There's a big display in the lobby, everybody sees it, everybody knows what it means, and everybody knows that if we're going to have a cloudy period of 3 or 4 days, the building's going to run differently for a little while than it does normally. But if you think about that and what we evolved for on Bill's stuff, we sort of evolved for wearing different things on different days. We sort of evolved for feeling different on different days, for moving. When our people feel a little chilly, which they do sometimes, they move to a different space in the office, which is warmer. When they feel a little hot, they do the opposite. There's no particular rule that says you have to be at the same desk every day. Now, a lot of people choose to, but it's a choice, and people are happier when they make choices, even if physically they're less comfortable. So we have a lot of choice in our building, and so there's a ton of education around that choice. And we also measure it, not with Bill's fancy headsets, although we'd love to do that at some point, but we take a fair amount of reads about where are we, how do people feel versus the other buildings that same group has experienced, how that compares with the norms from the CBE database, which is a good database to compare to. You will notice on office layout that they like their previous office layout more than the current one. That was a smelly, nasty old farmhouse with a rabbit warren of offices. But people got used to it. And at the point we did the survey, they weren't unused to it yet. And so you have a getting used to, unused to thing that colors what's going on as you start to get these human engaged buildings. We also used a much broader set of comfort definitions. It's not just what a thing on the wall says the temperature is. There's a whole range of things that people can do, most of which they can move. We have the heated and cooled seats that Blake mentioned. We were the inaugural customer for those. The ladies liked them, the guys didn't. They got a little uncomfortable. But I think version 2 is a little better. But we work surface temperatures, radiative heat transfer, we work air temperature, we work air velocity. You can control air velocity near where you sit. You can even have a little fan in your face if you're so inclined. Clothing level, metabolic rate, whether you're standing or sitting, changes a lot how comfortable you feel. And we have relative humidity, and we have all the sensors necessary, some of which we had to build ourselves with ping pong balls. So there's all this need versus used to on all of these dimensions. So our living lab partly is the building and partly the physical control of such a thing, which I'll get to in a second, but an awful lot of it is the living lab around the people and how the socio-cultural system teaches itself. The integration and automation, to go back to the mechanical engineering side of this, is extraordinarily complicated because it turns out the control world thinks that control is a knob that you turn up and down. At the end of the day, if there isn't a large machine in there somewhere that I can turn up and down to heat or cool, I don't know how to do it. And the way that we have to do things on purpose is if we know it's going to be a hot day the next day, which is normally the case nowadays, we have to look at the predicted temperature, we have to confirm the state of the building, we have to start pre-cooling it. At some point we have to stop pre-cooling it. All that is with automated windows. In the morning, we have to make sure that people don't immediately try to heat it because then it'll overheat. There's this whole degree of things around a distributed control system. I think we're on version number 3. We now have a bunch of intelligent, automated AI type algorithms. They don't work better so far, but maybe they'll learn.
It sounds familiar.
It's all part of the fun, and the people are into it by and large, and people have figured out where they need to be on what sort of day, and they cope. And not only they cope, but they're happy because they are in control of their coping. So I told you that a key part of this, because the building was, at least when we built it, a couple of standard deviations beyond the norm, we had to do a bunch of things in order to constantly emphasize for our team, and frankly our board, who pretty conventional board other than liking energy efficiency, we had to do a lot of things to continue reinforcing it. I probably gave a speech 50 times to members of the team about why we did not want them to build the building in such a way that when we sold it, it would look like everybody else's. We said, no, by the time we sell it, if we ever sold it, everybody else's will look like ours. And I had to say that endlessly, but it's already proving true as we see more passive house buildings, et cetera. So we had to get very, very, very specific about what our requirements were in a way that was quite different from what the norms were. And we also had to use our own variant of IPD. We paid a lawyer to rebuild the IPD contract so it would work for our sort of small project. That contract structure is freely available now on our website. And I think that's the end, other than there's a whole bunch of other things we could, and maybe we'll talk about in discussion if there's any time left, on other elements of what sustainability can do for you. And that's the end of my talk.
That's great.
Okay. Thank you for that presentation. I think it circled really nicely back to what Bill started with. And I'm struck with all 3 of your talks, what kind of different scales and different phases of the building life cycle you're talking about. Bill, you started talking about experience. Blake, you were talking about the construction phase. Hutch, you started talking about site and climate. So I guess the question I really have is at both ends of the scale, both when you start with the project, I guess really throughout the whole building life cycle, or project planning phase, from project planning to financing, to construction, to the users or the education of the users. What's the best thing that people could do? I guess I'm really asking you what your best job was. And I guess in some ways I'm also asking what the pitfalls are to avoid, but I'm not going to ask you what your worst job was. So in that sense, throughout this whole phase, if you kind of talk to each other in terms of your different, really approaches, what would you like other people in the team to help enable you to do your best work?
Team being the people we're involved with when we're...
Yeah, the team for the whole building.
Well, I'm finding that it's, and in my world at least, which is a fair amount of developer-driven projects. It's a different thing than, let's say, a direct institutional client. And Cornell was a hybrid. It was both the institution plus a developer that was actually delivering the project. In this case, the developer took a leap of faith, but also spent a fair amount of time investigating this whole idea of doing passive house on that building. And there was encouragement by the institution. But if I had to put it in a nutshell, I think it's to have building owners or prospective owners be open-minded about this approach. And everybody's going to ask, I'm sure a question will come up, so I'll preempt it, which is what's the return on investment if you're going to build passive house? It does cost more. The interesting thing, at least in our involvement so far, we don't have some hard statistics yet because it takes a fair amount of planning ahead of time, and we weren't quite able to do it in the huge rush that we went through producing the sort of the building for Cornell. To have a database where we had as close a comp as possible of another building about the same size, same location, same type, to the one that we were doing new, and then understand what was the cost difference going to be between the typical market-driven thing and a kind of a market-driven building, but with this added envelope and systems to produce the level of energy efficiency we're looking for. And so that's always the question, and I can just state sort of publicly that it's somewhere between It depends on the site, depends on the location, depends on the climate, but it could be anywhere from 3 to 7% difference in upfront costs.
Bill, are you anticipating the same question about the return on investment and experiences?
Yes and no. I mean, part of it is for us, and similar to these projects, first start with understanding who the potential users are and what their needs are. The second is, what does the site give me for free, right? Which is absolutely essential to Passive House as well. What is the site already doing? What does it already have? What are the assets that it supplies for me? And one of the things that Hutch didn't mention about the RMI building was that they were insistent that it come in at a market rate cost because they wanted something replicable. Amory's original house, the original building of the Institute, was amazing and fantastic, and was the inspiration for a lot of the original Passive House stuff from the guys from Germany who came over to visit it. But it was so exotic and crazy expensive and all of that when it was first built that it never actually got replicated because it was just, too different. And so what you're seeing with these buildings and the other work, and the stuff we're seeing with a lot of the biophilia work, is that they're coming in, they have to be market rate, and they have to be things that people are say, oh, yeah, I can do that. I can replicate that.
And so Hutch, in terms of saying to the team, the market would move towards the building you're building, I guess, are you seeing a lot of tangible movement in that direction? I guess what kind of gives you heart that the industry is learning these lessons?
I've seen tons of movement. Just the graph that Blake showed of more passive houses, not that passive houses is the only indicator by any means. We think that doing some of the things we did, maybe at more scale and maybe with less R&D during the process, frankly, A, it's a heck of a lot more fun. B, it gets you something that's a lot more future-proof. A lot of our costs had to do with things like ensuring that it was an institutional grade building that would last 100 years. We put it a foot or two above the 500-year floodplain, which meant we had to build it higher. Well, there's a pretty significant cost associated with that. There's a whole bunch of things that cost a bit more. In the end, Aspen's never a cheap place to build, but we did a whole bunch of benchmarking about it. And we did end up about 10% more in cost, so a little bit more than your benchmark. But we also have a bunch of people like me that are ex-business builders and scalers. So we went through and reverse engineered what all those costs were and why they were. Virtually all of those extra costs, because we were choosing to specify a system where we were one of the first in our geography, and in the case of our windows, the first in the country. We had to actually build our own supply chain for our windows because we couldn't get them from anybody. Well, that stuff scales. That stuff industrializes. And if I run those things down their curves, I get to where I'm frankly in the noise, in the statistical noise of what the cost of the building would be. And so over time, I do think that we'll see, as we've seen in other building classes, these deep green buildings can become incrementally, if not the same cost as something built conventionally without such attention. So it becomes a question of how do you apply the attention to it to get what you really want.
Steve, do we have time for questions?
Yeah, do we have time? Any questions here in the audience?
I'd love to make time for questions for the audience.
Do you have time?
I think we have a few minutes. Yeah, that'd be great.
We're a little late, but
Yeah.
I'll be right back.
We started a few minutes late. I think we have time.
We have a microphone?
Okay.
My name's Doug. I'm an urban planning student at MIT. Blake preempted one question about upfront costs. My question's about upfront costs, but from a slightly different dimension. For buildings that perform so well over their lifetime, are there any upfront expenditures or incremental energy intensiveness, either from building practices or from materiality, that we have to figure in our energy accounting over the building's lifespan? And are those incremental expenditures, if there are any, big enough for us to care?
So you're talking about like latent energy through
Embodied
the process
energy
of
is are the materials for the envelope more energy intensive than they are in more conventional buildings, those sorts of things.
Well, yeah, I mean, ideally, that's all taken into account. I guess just again, from my sort of niche, it's trying to put a dent in the way buildings are built now, given conventional sourcing of systems and materials. It's actually interesting because, Hutch was talking about, developing their own particular kind of thermally broken triple glazed window and all that. Well, there are actually some amazing products in Germany that have been around for a while. In our case, it worked well because it's a very tall building and we had a lot of windows, one for every room. So it's, 600 windows or something like that. So we were able to, buy those at scale and get a reasonably good price. So I'm not sure if that answers your question, but I think that, give it a shot.
I can give you a quick answer. I mean, you do want to do the math. And if you can, you use less steel and less concrete and more wood. So we have a CLT system, cross-laminated timber structure for much of the building. And so we actually have locked up a bunch of carbon. We do use thin layers of concrete for our thermal mass, but it doesn't take a ton of that. And we have very little steel in the building. But those numbers get totally dominated by steel and concrete.
Yeah.
And if you do think about steel and concrete, it's not that you don't use them, but the industry tends to overuse them. There's too much steel and too much concrete in most buildings. And if you put more attention into it, again, this attention and design intent and more analysis and more testing, you can get rid of an awful lot of that footprint. And there's work going on in the UK on that very actively now.
If you take a conventional Manhattan building, office building, over its lifespan, the embodied energy is less than 20%. It's 18 to 20%. You can see on our website a paper called Mid-Century on Modern, which was a study of how do you renovate the first generation single glazed office buildings in New York, and what would be the implication of demolishing them and replacing them, and the embodied carbon hangover, how long it took you to overcome that. But the energy use of, so the building we were looking at was a 1965 building. It could have been rebuilt more than 4 times over its lifespan because of the operational energy that it consumed over that lifespan. So embodied energy is important. And Hutchinson point too, we're doing research on some very large-scale timber structures now, and some stuff that, in particular, has been done by Arup and Mike Burke and some others, indicates that if your wood is sustainably harvested and the components are produced in a regional scale, you might actually wind up with components that sequester carbon through the entire lifespan of the building. That's new. That's never been done before. So the idea that you can have carbon balance within the fabric of the materials choices of the building itself is sort of the next radical edge. And Pliny Fisk in Austin is the one who's sort of been leading that research and conversation for a long time.
Great. So let's thank our speakers today.
Thank you very much.
Bill, Blake, David, and Hutch. Terrific session. And they'll be around to answer questions, and we'll be back in 10 minutes moving on to bottom-up real estate using street-level data for development decision-making. Really interesting work being done here at MIT.